Arc length. Let's jump into the formula for finding arc length. If f prime is continuous on the closed interval from a to b, then the length of the curve y equals f of x on the x interval from a to b is given by the integral from a to b of the square root of 1 plus the quantity f prime of x squared dx. Or we can replace the prime notation with dy dx. So the idea is that we are trying to find the length of a curve over this interval from a to b here. And we need the condition that f prime is continuous. And what that ensures is that the curve is smooth. So there's no sharp corners or breaks. So if that happens, we would have to split the curve into smooth pieces and then add the lengths together. Here's our first example. Find the length of the curve y equals natural log of secant x on the x interval from 0 to pi over 4. And we have a little sketch of the curve, which we can see is nice and smooth. We're going to have a differentiable function on this interval. And we're going to start to set up our integral here. So the arc length from 0 to pi over 4 of the square root of 1 plus, and then what's going to go inside these parentheses here is going to be the derivative of our function squared, and then we need our differential dx. So let's go ahead now and find the derivative of our function. So y is natural log of secant x. Y prime would be 1 over secant x times the derivative of secant x. So we'll put secant x in the denominator, the derivative of secant in the numerator. So we have secant x tangent x. Secant x over secant x is 1. So all we have left is tangent x. So that's what we're going to go ahead and replace over here inside our arc length formula. And then now we're going to go ahead and solve this definite integral here. So underneath the square root, I have 1 plus tangent squared x, which thankfully is an identity. So I have the integral from 0 to pi over 4 of the square root of secant squared x dx. And then the square root and secant squared simplify to just secant on the interval from 0 to pi over 4. So we're just integrating secant x. And this is one of those antiderivatives that we should know, which is natural log of the absolute value of secant x plus tangent x. And we're evaluating this from 0 to pi over 4. And now we substitute pi over 4 into each x, and then subtract substituting 0 into each x. So we'll have natural log, absolute value, secant, pi over 4, plus tangent of pi over 4, minus natural log, absolute value, secant of 0, minus tangent of 0. And so now secant of pi over 4, so we're thinking 1 over cosine of pi over 4, so 1 over rad 2, so that's just going to be radical 2. So I know I am skipping the evaluation of trig functions. Go back and review that. Definitely need to evaluate trig functions. And then tangent of pi over 4 is 1. And then minus natural log of secant 0, or 1 over cosine of 0. Cosine of 0 is 1. So this is going to be natural log of 1 minus 0. Tangent of 0 is 0. Well, natural log of 1 is 0. So all we have left here, our final answer, is natural log of the square root of 2 plus 1. I don't need absolute value bars anymore. This quantity is positive. So this is my final answer. It is, of course, a number because we're talking about the length of the curve. Let's revisit the arc length formula, but this time we're going to focus on if everything is in terms of the variable y. So let's say we have g prime is continuous on the interval from c to d. Then the length of the curve x equals g of y on the interval from c to d, which is a collection of y values. Then the length is the integral from y equals c to y equals d of the square root of 1 plus g prime of y as a quantity squared dy. Or we're taking the derivative with respect to y. So we're still interested in finding the same arc length, but now we're imagining that we're focusing on our limits of integration as y values and our function as a function of y. And so we still need the condition that our function is smooth, so we need the derivative of our function to be continuous for that to happen. In this example, I want to find the length of the curve x equals 4 rad 2 over 3 y to the 3 over 2 minus 1 on the y interval from 1 to 6. So here we have a function of y and y values that are provided as the interval. So here we do have a differentiable function that is going to be continuous. I could see the curve is a nice smooth curve. So what I'm going to do is jump straight to the formula here. So we're going to have the arc length is the integral from 1 to 6. And remember, these are y values. And then we're going to have the square root of 1 plus, and then I'm going to need the derivative of our given function squared. So I'm going to leave a blank space for that quantity squared, and the differential is dy. All right, so taking the derivative here, so x prime or dx dy, I'm going to leave the 4 rad 2 over 3 in front, and then this is just a power rule, so I'm going to bring the 3 over 2 to the front, y to the 1 over 2. The derivative of 1 is 0, so that's gone. And so here, 3 over 3 is 1, 2 divides into 4 2 times, so what I have is 2 rad 2 y to the 1/2 as my derivative that I'm going to substitute in over here. So I have 2 rad 2 y to the 1/2. And it looks kind of ugly, but remember that we're going to square this. And everything here is being multiplied, so I can square each piece. So what it's going to look like is we are ultimately integrating the integral from 1 to 6 of the square root of 1 plus, let's think about the coefficient here. So 2 squared is 4. Rad 2 squared is 2. So 2 times 4 is 8. We're going to have 8. And then we're just going to have a y because this 1/2 and this 2 multiply. So just y to the first there. And then just dy. And this is what we're left to integrate, which is not too bad. I'm going to go ahead and do a u substitution on it. I'm going to let u be 1 plus 8y. Then du is 8 dy. And so I'm going to go ahead and divide by 8 or multiply by 1/8. 1/8 du is equal to dy. And this is a definite integral, so I'm going to change my limits of integration to u values. So in other words, I have u of 1 is 1 plus 8 times 1, so u of 1 is 9. And then u of 6, 8 times 6 is 48 plus 1 is 49. So my new integral after the change of variables is going to be 1 over 8, the integral from 9 to 49, rad u, or u to the 1/2, du. And now I never have to go back to the y variable. I changed my limits of integration to u's. And now the antiderivative of u to the 1/2, so we're looking at 1/8, and then u to the 3/2 times 2/3, evaluated from 9 to 49. And here we can reduce the 2 over 8, that's 1 over 4, so I have 1 over 12, u to the 3/2, evaluated from 9 to 49. So we will substitute in 49, substitute in 9, and subtract those two quantities. So we're looking at, let's leave the 1 over 12 in front. We have 49 to the 3/2 minus 9 to the 3/2. And let's resist the temptation to use a calculator here. So what I'm doing is I'm taking the square root, let's focus on the denominator, the square root of 49, which is 7. So we made it smaller, but then we have to cube it. So 7 cubed is 343. So 49 to the 3 over 2 is 343. So I have 1 over 12. I have 343 minus, and here we can find the square root of 9, which is 3, and 3 cubed is 27. So we have 343 minus 27. So that's going to be 316. So we're going to have 316 over 12. And each of these is divisible by 4. So we're going to go ahead and have a final answer of 79 over 3. And again, we definitely need a numerical answer. We had a definite integral, and we're finding the length of the curve, the arc length. In this example, we want to find the arc length of 27y squared equals 4 times the quantity x minus 2 cubed from the coordinate point 2, 0 to 11, 6 rad 3. So this one's unique because our equation is not explicitly defined. It's not solved to be y equals a function of x or x equals a function of y. And we're not just given an x interval or a y interval, we are given full coordinate points. So what we want to do is decide whether we want to write this to be a function of x or a function of y. So on this example, I'm actually going to move forward with solving this to be a function of x. So trying to isolate y. I'm going to go ahead and start by dividing by 27. So I have y squared equals 4 over 27, x minus 2 cubed. And then taking the square root of both sides, which is going to give me plus or minus the square root of 4 over 27, x minus 2 cubed. But I'm actually going to focus on the positive one because if I look at the points that are given, I'm looking at this in quadrant 1. So I'm only going to focus on the positive one. So y is going to be equal to positive. All right, and let's actually take the square root of 4 and the square root of 27 and kind of simplify those coefficients in the front. So square root of 4 is 2. That's nice. And then the square root of 27, 27 is 9 times 3. And the square root of 9 is 3. So we're going to have 3 rad 3 on the bottom. And then we're going to have x minus 2 to the 3 over 2. So I'm changing the square root into that 1/2 exponent and then applying it here to the cube power. So it's going to become 3 over 2. So here is my y equals f of x function now. And I know I'm going to need to take the derivative of this. And I'm going to need to focus on the x values from my coordinate points, right? So this is our x value and this is our other x value because we just solved to be a function of x. So let's go ahead and take the derivative now. Y prime is equal to, let's leave 2 over 3 rad 3 in the front. And then we're going to apply the chain rule. We're going to bring the 3 halves to the front. 3 over 2, x minus 2 to the 1 over 2. The derivative of the inside is just 1, so that's nice. And let's see, some other nice things happen. 3 over 3 is 1, 2 over 2 is 1. So I get a derivative of 1 over rad 3, x minus 2 to the 1/2. So now we have our derivative, and we know we're going to focus on these x values for our limits of integration. So let's go ahead and set up our integral. Our arc length is going to be the integral from 2 to 11 of the square root of 1 plus, and then we're going to have 1 over rad 3, x minus 2 to the 1/2 all squared dx. All right, and so now, even though this does look ugly, it's not going to be too bad because I can go ahead and distribute the exponent because this is multiplication. So I have the integral from 2 to 11, the square root of 1 plus, we're going to have 1/3 x minus 2 dx. That's it, right? Because again, 1 over rad 3 is just 1 over 3 when you square that, and then that 1/2 and that 2 multiply together. So let's clean up what's underneath this radical here. So we're going to have the integral from 2 to 11, the square root of Here I have 1 plus, if I distribute the 1/3 in, I'm going to have 1/3 x minus 2/3. So I'm going to write this as 1/3 x first. And then I'm going to have, again, that minus 2/3 plus 1. So it's just going to be plus 1/3 dx. And here we can go ahead and do a u substitution on this. So I can say, let's let u be 1/3 x plus 1/3, and then du is just a third dx, or 3 du is equal to dx. We can change our limits of integration and turn them into u values. So if I substitute in a 2, I'm going to have u of 2. That's 2/3 plus 1/3. Well, that's just 1. And then u of 11. So we're going to have 11/3 plus 1/3. That's 12/3, or 4. So our new limits of integration will be from 1 to 4. We'll have a 3 in the front here. So we'll have 3, the integral from 1 to 4 of the square root of u, or u to the 1/2 du. And I'm going to make some space. Now we're going to have the antiderivative of u to the 1/2 is u to the 3/2 times 2/3, evaluated from 1 to 4. So let's see. The 3 times the 2/3, that's just going to give me a 2. So I'm going to have 2, and then I'll have 4 to the 3/2 minus 1 to the 3/2. And here, 4 to the 3/2, the square root of 4 is 2. 2 cubed is 8. So what I have is 8 minus 1, which is 7. 7 times 2 is 14. A nice integer value for this arc length. Before moving on, I just want to go back up to the original problem and kind of mention that we could have done this another way. So I elected to solve for y to be a function of x. But here I could have solved for x. So I could have divided by 4 and then taken the cube root of both sides and then added 2 to the other side to solve for x to be a function of y. But then I would have needed to use the y coordinates of my points over here. So 0 and then 6 rad 3. So that was an alternative option here in order to find the arc length. Let's take a minute to explore the formula for arc length. I kind of just gave it to you earlier and didn't really talk about where it comes from. So let's just briefly talk about where this comes from. So we're going to go ahead and sketch a little curve. Let's say this is y equals f of x. And again, we want the length of that curve from sum a to b. So let's go ahead and focus on a here. And let's create a subdivision at, let's say, this point here, x1. And let's go ahead and draw the corresponding point at x1 here. And let's focus on finding the distance between these 2 points. So let's say the distance between this point here, which would be a y of a, and then x1 y of x1. So how do we find the distance between 2 points? It's not the length of the curve, but the distance between these 2 points here. Well, we have a formula for that from our past courses. So we know the distance between 2 points in general is the square root of x2 minus x1 squared plus y2 minus y1 squared. So our coordinate points here are a, y of a, and x1, y of x1. So this formula would tell us the distance between these 2 points here. And what we could also do is, create another straight line distance between x1 and b. So we can go ahead and say that we are interested in finding the straight line distance here that goes from x1, y of x1 to, let's see, this one here is going to be y of b. And we can use this formula again, and we can add those two distances together. That's going to give us a pretty nice approximation. But what we want to do in calculus is we want to make this precise and we want to chop this up into a lot of different subdivisions, right? And add them all up. So the arc length, if we did that, would be approximately still. If we're adding them all up, we're going to use a sum. So let's say the sum of I equals 1 to n. So this right now, this is like our first subdivision. Let's call it delta x1. So this is the first change in x. We'll call it delta x1. It's the first change in x. And this is like delta x2. And if we divided it into a bunch of little tiny subintervals, there'd be n of these. And then there's the corresponding delta y's, the change in y's. This is delta y1, and this would be delta y2. So here I would be adding up this distance formula, but here's how I'm going to write it. I'm going to write it as all of these delta x sub i's squared, and then all of these delta y sub i's squared. So if I add all of these up, if I take a bunch, if I divide this into n subintervals and I add them up, it's going to be a pretty good approximation. Depending on the n value, the higher n I choose, the better approximation that it's going to be. But what we want to do is, make it more precise. So I'm going to do kind of this little algebraic trick here. So what I'm going to do on the outside of this square root is I'm going to introduce delta x sub I over delta x sub I. So this is really like multiplying by 1 in a clever way. And I'm going to leave this delta x sub I in the numerator alone. But what I'm going to do is bring this delta x sub I into the square root. In order to bring it into the square root, I'd have to square it. So in other words, my next line here is going to be the sum of I equals 1 to n. I'm going to make the square root taller now. So I have delta x sub I squared over delta x sub I squared plus delta y sub I squared over delta x sub I squared. And now I have the delta x sub I left on the outside. So the delta x sub I in the numerator, I left there, but what I did was I brought the delta x sub I into the radical, but then I would have to square it because I'm taking the square root, and the square root squared gives me just the original. Okay, so why did I do that? How does that help? Well, delta x sub I squared over itself is just 1, and maybe you can see our formula starting to take shape. So the sum of I equals 1 to n of the square root of 1 plus, and now I'm going to have delta y sub I over delta x sub I quantity squared delta x sub I. Okay, but this is still an approximation. What we want to do is introduce the limit to formalize it into an integral. So if we take the limit as n approaches infinity of this sum of I equals 1 to n of the square root of 1 plus delta y sub I over delta x sub I quantity squared delta x sub I. Well, now as n approaches infinity, we're going to have an integral. The integral from our formula, a to b, the square root of 1 plus, so this instead of delta y sub I, delta x sub I, this is going to become dy dx, the derivative squared, and then we'll have our differential dx. So this isn't really rigorous. It's just to kind of explain that this formula is really coming from the arc length and chopping up the interval into tiny subpieces and then taking the number of subdivisions to infinity to explain where that comes from. Rigorously, we would need to think about the mean value theorem and talk about how in each interval there's exists some I where the slope of the tangent line is equal to the slope of the secant line. So we would need some more formality, but at least it gives you an idea of where this formula comes from.